Good afternoon. Thanks for showing up. I was here yesterday. I presented twice, and seems like everybody's having a good time and learning a lot, so happy to be here. Tell you a little bit about myself. My name is John Bento. I've been in education for about 25 years. I was a machinist mate in the Navy for 6 years, so that's my let me tell you about R12 and all the damage I did to the planet by releasing all that stuff way back in the day. I taught chemistry and physics for a bit for high schoolers, and then I wanted a real challenge, so I started teaching adults because teenagers are actually easier sometimes. Most recently, I worked for General Electric. I was a diesel engine instructor and an electric troubleshooting instructor for their locomotives. And for the last 2.5 years before I hired on at Hussman, I was working in the field in beautiful Galesburg, Illinois. GE was fun. They sent me all around the world. It's where I met my wife down in Mexico. So that's me. So moving on to today's topic. Initially, we were just going to do a deep dive and very technical on transcritical, but then I was speaking with Danielle, and she said that a lot of the attendees don't have a lot of experience with CO2 because it's kind of a newer refrigerant. Show of hands, how many people have worked on transcritical or Cascades? Okay, so not so bad. All right, well, that's a heck of a lot more hands than I got in 2 sessions yesterday. I think I had 2 at the first and 1 in the second. So we're still going to talk about those things, but I altered the curriculum just a little bit different, and just to sort of explain why we're at this point where we're seeing all this CO2 happening in natural refrigerants. Back in time, let's return to a simpler time when none of us had a job because we cut ice out of frozen lakes and threw them in ice boxes. This was refrigeration in the 1800s. During the Industrial Revolution, they started coming around with the mechanical refrigeration, and primarily this was for ice production, okay? There was literally no air conditioning. Air conditioning wouldn't come along until Carrier in the 30s. But the choices of refrigerant were dubious at best. Ammonia, that's still used today quite a bit. We got any ammonia jockeys here? All right. So why is ammonia a poor choice for residential cooling? It stinks. It's self-alerting. Yeah, we know that. It's not? I thought it was alerting at 35 ppm, if memory serves.
About 2, depending on the person.
Depending on
somebody that never smelled it at 1 ppm, they're running out.
Exactly. So the downside to ammonia is it will melt your face off. It is anhydrous. Without water, it's a hydrophilic chemical. So when it is released, it will immediately seek out moisture. That will be your mouth, your nose, your eyes, your crotch, your armpits, and then it'll just start eating the rest of you. Methylchlorine, I can point you to some documentaries on World War I and about the effects of chlorine gas on human lungs. Sulfur dioxide, I believe, has an OSHA limit of about 4 ppm. These are really bad choices, guys. These are not good choices. CO2 was used, believe it or not, starting in the 1870s. And it was used quite frequently in marine applications, keeping stuff on cargo ships cold. The reasons being because of the toxicity of these other choices. As a former sailor, I can tell you, we work in enclosed spaces, and we don't want any of this stuff anywhere near us, okay? Nor should anybody. But chemistry to the rescue, believe it or not, it was not DuPont, it was General Motors. They owned Frigidaire at that time. DuPont later bought the brand from them, but they came up with synthetics. We wanted a safe, non-toxic, non-flammable refrigerant. And the gentleman that created it, R11 was his first creation, then R12, R22, R21. Now, all the pieces are coming together right now. We have a safe, non-toxic refrigerant. We have the Great Depression. We have the Works Progress Administration. We're building dams. We're electrifying rural communities. Holy crap. Can you imagine all the dollar signs people are seeing if we can put a refrigerator in everybody's house? A mechanical one that runs 24 hours a day? So perfect place, perfect time. They did as advertised. R22 is an incredible refrigerant. It still is today. The laws of physics have not changed. But synthetics are sort of a victim of their own success. They are highly stable molecules, which means they don't break down when they're released. They just float around in the atmosphere until they get high enough up, where solar radiation is powerful enough to break them apart, and they then combine with our ozone layer and destroy it. We discovered this in the 80s. Everybody got together, said, hey, we got to get rid of these things, okay? Because not only were we using them for refrigerants, we were using them for propellants. If people my age or older remember, underarm deodorant, hairspray, anything pressurized that came out of a can, there was CFCs behind it. And we're just dumping it into the atmosphere. So they got rid of all that. They said, we fixed it. We saved the earth. Yay. Good on us. And then global warming happened. All right, so next crisis. So now we realize that, and this is when we talk about CO2, everybody's like, well, on the news, all they talk about CO2 is a greenhouse gas. And that's a true statement, it is. But what we found is that depending upon the structure of these refrigerants, some of them are really good greenhouse gases, okay? And what that means is that they trap outgoing radiation. So if you keep putting energy into a system, it's gonna get hotter, it's gonna get warmer, it's gonna get more energetic. So they came up with what they call global warming potential. CO2 being a naturally occurring gas in our atmosphere is given a 1. GWP of 1. Our old friend R12 here, 10,600. So what does this mean? This means that in my misspent youth in the service of the government, if I released 1 pound of R12 into the atmosphere, that would have the same global warming impact as releasing 10,600 pounds of CO2. Yikes. And our old buddy 448, he's a good one, R22. So we're starting to phase these out. And in 2020, Congress passed a bill called the AIM Act. And it has to do with like innovation and manufacturing, something. Bottom line is, so last year, the Supreme Court said, EPA can't tell power companies how to regulate their emissions. It's EPA versus West Virginia. Because Congress had not specifically told them they could do so. Well, now Congress has specifically told the EPA they can regulate GWP and synthetic refrigerants. So, if we look at the GWP's limits that go into effect on 2025, find me a refrigerant that's lower than 150. Find me a synthetic. It's not going to happen. Okay? 513A, I see these in Cascade systems quite a bit. They're the closest you're going to get. 134, 448. Hy-V, if anybody's from Midwest, Hy-V's using 449. So what are our choices? We got 717, ammonia, we got CO2, and we got propane. So that's why you're seeing all these CO2 systems coming into the market. Any questions so far? Didn't think you were coming to a history class, eh? All right. So, CO2, the main attraction. Like I said, it was very, very popular back in the day. And then synthetics showed up right about here, and then you saw the gradual drop off. The reason for that is CO2 is kind of an oddball as a refrigerant. It's really good. It's got a lot of positives. It does have some negatives. At that time, and even today, one of the big challenges is a very high pressure. Okay? On a transcritical plant, our high side compressor discharge can be up to 1,500 psi. But it's good for the environment. So what are its benefits? Like I said, low GWP, high vapor density. What does that mean? Basically means I'm going to save money on piping. I'm going to save money on smaller compressors because it has a higher refrigeration capacity because of the density of it. You look at a transcritical rack, you're not going to see many pipes bigger than 5/8. It has about a 33% higher density than R22. So we can cool a lot more with it. CO2 is cheap. $1, $1.50 pound, depending on where you're at, as compared to synthetics. Another bonus is your job just got easier. You don't have to reclaim this stuff. Just like in Frozen, just let it go. Let it go. All right, same with propane, let it go. Don't have to worry about it. Again, excellent, it's got excellent heat properties due to its physical nature. It's really, really outstanding for heat reclaim. So coming off that high side compressor discharge, we're looking at 200 to 300 degrees Fahrenheit. So if you're up in the higher latitudes or colder climates, you can actually tweak your system to take advantage of that high temperature and use that energy. Again, physical stability and safety, non-flammable, non-toxic, heavier than air. OSHA limit for exposure is 5,000 ppm. For large CO2 racks, we're going to have in machine room or in large walk-ins, we're going to have some leak detectors. Generally, we recommend maybe set around 3,000 ppm. Another nice thing about CO2 is it's easy to find a leak on the low side or on the liquid side. You want to know what? Anybody? It's snowing, baby. It's snowing. And I got a cool video later, and that's one of the things that's a little bit different about CO2 is how we charge it, how we handle it, how we put it into a system. Challenges. Right now, gas availability is challenged. Anybody have trouble getting any CO2? Yeah, it's tough. When we talk about purity, Hussman recommends anything above bone dry. That is 99.8% pure. Refrigerant grade or Coleman grade is 99.9. The reason for that is, and that's one of the things that's leading to this shortage, okay? Because we need super clean bottles for this. This isn't industrial grade. We don't want any moisture in those cylinders because carbon dioxide has this nasty habit of reacting with water and forming carbonic acid, which is it's an acid. So it can degrade your piping. Material considerations due to those high pressures I talked about. What's K copper? What's it rated at?
Depends on the size of the pipe.
Ballpark it for me.
1330.
1330.
Depending on the size of the pipe.
So for a large pipe.
Yeah.
Okay. How about for a small pipe? Remember I said one with 5/8. Well, that may be true. According to my research, it's around 700 PSI.
Okay.
Yeah.
Well, it depends if you're running a Mueller streamline or just a regular type.
Leave it up to me to get the two material scientists in the. No, and I'm very thankful for this. Absolutely. Yeah, I said 700 pounds yesterday twice, and nobody said boo. So obviously it depends on it. But with 1,500 pound discharge, it really doesn't matter, right? Yeah. Okay. All right. So we have material considerations. No, and that's great. I'm happy to hear it. That I know what I'm doing when I get back to the hotel. Yeah, because I'm a nerd. So material considerations. Right now, Hussman does not have transcritical racks fully made by Hussman. We partnered with LMP, which is a Canadian company. And Canada has a rule for their high side. You have to use stainless steel. Okay. In America, there are other options. It's called XHP or K65 copper, and those are strong enough. The problem was, what's the problem with stainless steel? Expensive. You have to actually weld it. You got to weld it. You can't braze it. Yeah, all those wonderful things. And you have to have a pretty good welder. Now, those ammonia guys, you probably got a couple welders on payroll, but if you're an old DX cowboy, I don't know, but what happens on the roof stays on the roof, you know? That's all I'm saying. So that is it. That is a consideration that we have. So if you see a Hussman transcritical rack for the next couple of years, you're going to see inside the rack, it'll be stainless, and then when they run to the gas cooler, they'll switch to that alloyed copper. More electronics, CO2. We need very quick response times on CO2. So on a transcritical system, each of your cases is going to have an individual EEV on it and a case controller. So that adds to your startup cost. Sometimes you have a higher initial cost. And the big thing for me is technician familiarity. Now, you guys, a lot of you guys have the CO2 experience, but like I said, yesterday out of 75 people, only 3 raised their hands. And you just have to look at the system a little bit differently. We're still doing the same thing. We're making stuff cold. We're using pressure and temperature to do it, and we're using a chemical. Okay? If you keep that in mind, we'll all be laughing. We got 2 main types of systems. Cascades. Cascade is going to use 2 refrigerants. Could be glycol, could be ammonia. In HEB's case, they decided on 513. You have a primary refrigerant, which will be a synthetic or another natural, and then you'll have a secondary, which is CO2. CO2 is going to take care of keeping the ice cream and the frozen foods, all your low temp load, and the synthetic, I'm just going to refer to it as synthetic. I know it can be ammonia, which is natural. We'll just say synthetic. That's going to take care of your medium temp load, and then we're going to have some plate heat exchangers called Cascades, and that medium temp refrigerant is going to condense my CO2. So in theory, those 2 refrigerants should never, ever physically touch, in theory. Okay. The other one is transcritical. You might hear them called booster systems, whatever. This is 100% CO2. It's going to handle both your low and medium temp loads. Initially, this was limited to colder areas for efficiency reasons. This is sometimes you'll hear a pushback from a lot of people about CO2 and the energy penalty, but there are ways that we can improve efficiency for these, and so that whole transcritical equator I talked about, personally, I think that was you know how when they have the oil companies do the environmental studies? I think DuPont did this study, you know? So, and we'll talk more about efficiency at the end. But let's talk about Cascade operation. So here's just a basic Cascade system. We'll talk, and this is very, very basic. We'll talk about some key components you might find with them. But again, here's my primary loop. Running a synthetic, I'm just gonna say 513, we'll be done with it. Goes through the condenser, goes in the receiver, goes to your medium temp evaporators, comes down here, goes into your Cascade, condenses my CO2, okay? So everything above here, you guys know. This is just a regular old DX synthetic side, okay? No difference, don't be afraid. Heat exchanger, 1, 2, or 3, it depends on the customer, as most things do. Customer is always right. Customer writes the checks. This is why technicians are angry when they can't service or repair things, because they have to be like that guy in the Fantastic Four with the bendy arms. Yeah, of course, it'd be great if I could change out my temp right filter without having to go through the top of the rack. But engineers don't care, and accountants sure as hell don't care. So, so unfortunately, you're left to deal with it. I can say on the LMP transcritical racks, you can change those filters from the side. You don't have to go in through the top. There's enough room. This is very attractive for hot climates. So just because of the properties of synthetics, we can just reject a lot more heat than we can get out of CO2. Piping diagrams. I love my piping diagrams. They are very, very valuable. Now, back in the Navy, when you walked into any engineering space and you had to trace out a system, you would hand over hand it, go to each valve, and each valve had a wonderful little tag on it. It had a designation, and it would kind of tell you what it did, you know, like evaporator suction or whatever. We don't do that. So when you get a rack, any install or startup people here? Mostly just service, so, okay. But wouldn't it be nice? You're dealing with a new technology, these transcritical racks, both your low, all your lines are going to be insulated, liquid and vapor, okay? Yeah, there's a ball valve, but what is it? There's directional arrows. So what I'm trying to get Hussman to do is start to apply some labels in the factory. So when you guys get a hold of them, they're going to wear off, but hopefully it'll make your job a little bit easier. For this particular one, got our liquid suction heat exchanger here to manage our superheat for our CO2. For these PID diagrams for Cascades, the CO2 is always going to be in pink, and your primary refrigerant will be in black, okay? And again, this liquid suction heat exchanger, it goes ahead, adds a little bit of subcooling to my CO2, my liquid CO2, and adds a little bit of superheat to my compressor suction. So nothing new there. The de-superheater, okay. And this is where things start to get a little interesting. So, as my CO2 comes out of my compressors, it is hot. We don't want it to be too hot. We don't want it to be too cold. So this is our Goldilocks right here, the de-superheater. I want to run, coming off this temperature sensor right here, I want to make sure that my CO2 is somewhere between 95 and 105 degrees Fahrenheit, okay? That sensor is going to talk to this three-way valve right here, okay? And then that three-way valve is going to either run, if it's too hot, it's going to run that gas through that de-superheater, and then off it goes to the Cascades. And if it's too cold, it's going to go ahead and throttle this closed and open up this bypass, and off it goes. The reason we want to maintain a reasonable temperature, especially on the too cold side, is you can actually get some condensation in that line. And if you send liquid CO2 into your Cascade heat exchanger, it's going to screw up the operation of that rack, okay? Because you can't remove any more. You can get a little subcooling out of it, but the whole point of that heat exchanger is to condense it. So if I send a liquid in, I'm not moving enough heat, and it's going to affect my medium temp side. These are what the valves look like. Be careful. Make sure they're piped and programmed properly. On the older racks, you'll see this. On newer racks, you'll see this. All this little extra down here tells you is that it's a serviceable type, okay? If this is improperly piped, and again, when you're doing startups and you're checking, you know, the brazed-in check valves are wonderful. One guy from CoolSys told me that they had 14 of them that were installed backwards at the factory. So, yay. I'm not saying it was a Hussman rack. Not saying that. We got enough issues with CoreLink, right? So, all right. Like I said, Cascades, here's our main heat exchangers. Again, nothing new here. Just a standard plate heat exchanger. Another one of the reasons, so we talked about if we have too low a temperature on my CO2, we don't want that condensation coming in. If it's too hot, the laminate that they put these plates together with is subject to thermal stress. So they say. Is it going to happen in 2 weeks? No. I mean, there's a store down in Texas that was running 150 degrees going into the Cascades for a month, and it didn't happen. But again, we want to try to maintain that 100, 105, 110 degrees going in just for overall operation of the Cascades. Another thing we have is the auxiliary condenser, all right? This is primarily for our CO2. One of the differences of CO2 is, so everything is going to go ahead and increase in pressure as temperature increases. Well, CO2 does it very, 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 very quickly. So the pressure increase per degree for CO2 is much higher than any synthetic, okay? So in the event of a power failure, this guy's hooked up to our EPS, emergency power supply, emergency power system, whatever you want to say. And basically, it's going to go ahead and take this CO2 coming out of our vessel and run it through this auxiliary condenser to keep it cool. So that way, we're not going to lift our 650 and lose a bunch of CO2. So again, if you lose power like this morning, no biggie. But if you're down in Texas or out in Palm Desert and you lose power at 2 in the afternoon, you're going to need that. Another thing when we look at our CO2 compressors, again, the reason I'm focusing on the CO2 side of this is because, like I said, for your medium temp, they're just nothing you haven't seen before. Your oil devices for your medium temp are Sporlins, the old floats. CO2, because of the higher pressure, is going to use these Emerson jobbies. They got LED lights here, so you got a green for power. You got a yellow saying I'm low on oil. I'm going to activate solenoid, fill it up. And they got a red one. If it goes red, it means I've asked for oil. I still don't have enough oil. Once it gets enough oil, it'll go back to yellow, maybe back to green. If it does that 5 times in 30 minutes, that compressor is going to shut down and manual reset only. So it gives you a little bit of wiggle room if you're having oil delivery problems, but if it does it 5 times, if it goes red 5 times in a half an hour, the next time it's going to be flashy red and you're going to be on a service call. Suction filters. Here's another thing about CO2. Recommend to leave CO2 suction filters in after startup and change them as preventive maintenance requires. Okay? Why? Anybody? In a study done by the Suction Manufacturers of America. No, actually it has to do with the chemical properties of CO2. CO2 is very, very good. It's oil is extremely miscible in CO2, much more so than in synthetics. It also is a very good cleaner. So if you have somebody at the factory, at any factory, who's brazing and they're not putting a nitrogen charge on there and you're getting a lot of soot and a lot of crap in those lines, that CO2 is going to pick that up. So that's why. And I know when you start up a regular system, you have those filters in there, and once you're up and running, you take them out, everything's hunky-dory. But because of CO2's properties, of its ability to pick up any kind of crap, we recommend that you keep these in and change them when you do your regular filter changes. Charging CO2. You need two different kinds of bottles for CO2 charging. You have a gas bottle, which may or may not have a cap charge on it of nitrogen or argon or some, non-reactive gas. That's what we're going to start with. We're going to dump gas into our system when we charge it. We cannot dump liquid into a flat system. And the reason for that goes back to the properties of CO2. CO2 cannot exist as a liquid below 75 psi. Now, Hussman says pressurize it with vapor up to 150, and that's just to make sure that nobody could screw it up. But as a former physics teacher, I will tell you, once you're above 80 psi, you can start dumping liquid in there, okay? If you try to dump liquid in before that, because it cannot exist as a liquid, it's going to turn to a solid, like that, okay? So two different types. These cylinders, they weigh about 90 pounds. They got about 50 pounds of refrigerant in them. They empty pretty quick. Some customers will want you to have a filter coming off the bottle. Depends on the customer. So here's a really good visual example of what I was talking about when we try to charge a system with liquids.
If we raise the pressure, we can put the dry ice, we can put the carbon dioxide in a place where it can exist as a liquid. Going to seal it up so that the gas cannot escape. Because the gas can't escape, the pressure inside of the tube is going to go up. When the pressure inside of the tube reaches about 5 atmospheres, the dry ice reaches a point where instead of going directly to gas, subliming, it can melt. It can turn from a solid to a liquid. Now what's going on right now is heat going into the tube is causing the dry ice to sublime. As the gas builds up inside of the tube, the pressure goes up. And as the pressure goes up, there it goes, the dry ice now can melt. Now we have mostly liquid, and if I release the pressure, the liquid carbon dioxide can no longer exist as a liquid. And because it's still cold, it condenses straight back into a solid.
So there you go. That's one of the oddball things about CO2. So again, you just got to be aware of that when you're doing that charging. Any questions on that? Yes, sir.
When that happens inside the system, what's the corrective actions for it? I mean, obviously.
Cue the Jeopardy music.
Nobody's gonna do this.
You just kind of gotta wait it out, because we're at atmospheric and there's only two choices. You got dry ice or you got gas carbon dioxide. So you got to wait for it to sublime. No torches, no torches, no torches.
You can't add 100 pounds of vapor and bring it back to liquid? Like, you can say you're.
If you can get the vapor in there. Yeah, if you can get the vapor in there. If you have that dry ice formation and you can't get the vapor through, you got to wait on it. But yeah, if you can reestablish that pressure, that CO2 will liquefy again. Thank you for bringing, so does that answer everybody? Okay. All right, transcritical systems. Again, just a basic, generic. We got two compressor groups. Got a low temp, and I call them the medium temp. This is our low side, this is our high side. You'll notice we have various pressures here for discharge. This is going to be dependent upon my ambient temperature. And again, this is one of the weird things about carbon dioxide. It has an extremely low critical point. So like, what's the critical point? What is it? Anybody got a critical point for one of the synthetics? 150, 160 degrees Fahrenheit, right? So where on earth is it 150 or 160 degrees outside? Nowhere, okay? Well, CO2's critical point is 87.8 degrees Fahrenheit. So that means when I'm working in Palm Desert or Phoenix or Houston, it's going to be hotter than 88 degrees. So that means my carbon dioxide will not condense in the condenser. You're shaking your head ruefully, sir.
And I'm thinking, thinking Back to the Future.
Still? From the first slide?
80 degrees.
Yeah, 1.21 gigawatts. So if we look at our Molière, or our enthalpy diagram for CO2, you'll see right here, that's where that critical point is. So I have my standard, refrigeration cycle here, evap, a very little bit of superheat. Then we're going to compress it. Now, if I stay below, so on a regular synthetic, I'll compress it up to about here, and then I'll run it across. Once I get below this dome, then I go back into saturated. I start to get condensation in my condenser. Then I get a little bit of subcooling, and then back to my expansion. So if I look at transcritical, here's a standard subcritical. So if it's 50 degrees outside, this is what my refrigeration cycle is going to look like with CO2. If it's 95 degrees outside, I am compressing this way, way up to where when I go through my condenser, I'm removing sensible heat only. Because it stays above that critical point, I cannot get it to change state solely by removing temperature. So that's what transcritical operation is, okay? That's why we refer to the condenser as a gas cooler on a transcritical rack. Because when it's running in transcritical, we're not getting any condensation coming out of there, okay? I'm going to cool it, I'm going to remove heat, but I can't get it down to a liquid just by removing heat. So what I end up doing is I have my throttling valve right here, and that's going to force a pressure drop, and then I'm going to get a mixture of liquid and vapor CO2, okay? Again, how much liquid, how much vapor? That depends on what my gas cooler outlet temperature is, okay? The lower it is, the more liquid I'll get. The higher it is, the more vapor I'm going to get. This generally, it could be 70-30. This is in transcritical operation. Remember, it's hot outside. It's going to be a mix, okay? And the problem is, if it's super duper hot, like Phoenix, 50-50, I'm getting 50% liquid and 50% gas. I keep dumping gas into this flash tank. What happens to the pressure? Goes up. Got to get rid of that. 650 is my relief. So at 480, this flash gas bypass is going to open. I'm going to take this vapor and I'm going to dump it back into my medium temp suction. Okay? This is the big energy penalty they talk about. When it's super hot outside, if I'm running at transcritical, basically I've compressed 100% of my refrigerant, but I'm only cooling with 50, 60, or 70% of it. Okay? Think of flash gas as the crappy kids on a football team. They take up seats on the bus, they eat food, they take up uniforms, but they don't do jack squat to win the game. Okay? And I should know because I was one of them. So that's the big knock. When we look at troubleshooting a transcritical system, we want to look at that flash tank operation. Flash tank pressure is what drives this entire system. Okay? Keeping this around 480 psi. Okay? My liquid CO2 is going to be at about 30.5 degrees Fahrenheit. That's an oddly specific number for approximately, but I apologize. So, on a hot day, this guy's going to open up, and I'm going to dump this very cold vapor into my medium temp suction. This is another thing about transcritical systems. My medium temp compressor suction is getting refrigerant from 3 different sources. I'm getting it from my low temp compressor discharge. I'm getting it from my medium temp evaporators. And on hot days, I'm getting it from the flash gas bypass. So we have 3 sources of gas, different temperatures, different volumes, and somewhat, maybe a little bit different pressure. Like I said, this guy's jumping in at 480. My low temp discharge is going to be about 415. My evap discharge is going to be about 400 psi. So I have different pressures, different temperatures, and different volumes that are constantly changing with my ambient temperature, with my defrost schedule, all those things. So that's the big deal when we talk about how to manage a transcritical system. Flash tank pressure, and then making sure we have proper superheat control on our medium. Low temp compressors, don't worry about it. Now, we never say never, right? But the chances of a low temp transcritical compressor slugging for liquid floodback is about as good as my Cleveland Browns winning a Super Bowl. Not going to happen, ever. These systems generally, with this liquid suction heat exchanger, by the time it makes its way to this compressor suction, you're at about 40 degrees of superheat. Okay? Another nice thing about the CO2, when I talked about smaller components, has anybody ever seen the low temp compressors on a transcritical system? They're babies. They're tiny. They're tiny. Again, part of this is due to the vapor density of our refrigerant, and another thing is our compression ratio is like 2 to 1. So there's just not a lot of work that's going on. They're real quiet. They don't vibrate that much. So yeah, the low temp side really takes care of itself, once it's up and running. Medium temp, because it's so susceptible to what's going on outside, that kind of demands our attention. Let me see. As I said, superheat control, super duper important for these transcritical systems. This diagram is missing. There's a valve down here as well. And basically, we're shooting for 36 degrees Fahrenheit superheat in our suction. If it's too low, like I said, CO2 is a big fan of oil. Oil's very miscible in it. It's going to start pumping oil. If it's too high, we're going to get hot oil, degraded lubrication, and compressors don't like that. So what will happen is we'll measure that superheat and use this heat exchanger. If my superheat is 40 degrees Fahrenheit, this bypass valve is going to be wide open and this valve is going to be shut. If my superheat's too low, this guy's going to close off and this guy's going to open up. And again, it's a direct proportional relationship. If this guy's 30% open, this is 70% open, okay? And then I can go ahead and add some extra superheat from coming off my gas cooler. Now, can I have a system that has a hot gas dump on it?
Yeah.
Sure. What's the benefit of a hot gas dump?
You dump and discharge directly into the cycle.
Yeah, it's cheap. They've been doing it for decades. Everybody knows how it works. The thing about this is it's kind of imprecise, though. Hot gas dump is like using a hand sledge to put in a finishing nail for molding. It'll get the job done, but it's not going to look very pretty. So again, this is going to be a customer decision. Obviously, with this heat exchanger, you're going to have extra piping, extra valving. So, you know, again, customer decision. Most all the racks that I've seen that are running for Target, for Transcritical, they do have this heat exchanger instead of the hot gas dump.
You can also use those valves to stage the load as on a restart of the rack. With that heat exchanger, you can actually throttle down both of those valves
Yeah.
and step them up in stages as it.
Well, yeah, and when you recover from a shutdown system, you have to get this medium temp load up first. You have to. Because if I start up my low temp load, what's going to happen? These compressors are going to trip because there's nowhere for the discharge to go. And now we just got the nice little animation that my my big boss said. She loves animation, so she's like, make sure you put the animation in there. And then we have our liquid going to our coils and our discharge joined by flash gas into our medium temp compressors and then through the gas cooler condenser. Now again, like I said, the higher the temperature outside, the higher my discharge is going to be. Temperatures, discharge temperature 200 to 300 degrees Fahrenheit, so be careful, you can get burned with that. Let's see, 2 weeks ago I was down in Texas. It was a nice cool day, probably about 60 degrees. Our discharge pressure was about 1,000 PSI. And that would be operating in subcritical. So now again, in subcritical, if it's 60 degrees, let's just say, I am going to get some condensation in here because I'm not above that critical point. So in the event of cold, and there's various strategies. Like one of the other presenters that I sat in on, they like to use CO2 a lot for heat reclaim. So sometimes they'll force it into transcritical mode so they can use that heat reclaim. For most of who I've dealt with here in the States, like out at our Chino branch or down in Texas or in hotter climates, it's all about limiting the amount of hours you're in transcritical because of that energy penalty. All right, here's that wonderful photo about the transcritical equator. And again, efficiency limits of transcritical CO2. Anything south of here, anything north of here. And again, I call BS on this because my wife's from Mexico City and I don't think I've ever been there. It's never been above 85 degrees. It just doesn't get that hot there. So And the simple truth is that Palm Springs is running a transcritical unit, and it's running in subcritical at about 95% of the time. So when you talk about an energy penalty, if you're running transcritical for maybe 300 hours a year, is it really going to ding your electric bill that much? Probably.
You're talking air-cooled gas coolers.
Ah, no. I'm talking, we're going to get to that. Did you look at my deck? No, there's improving efficiency. That's just what this gentleman was talking about. So how do we achieve that? How do we reduce the number of transcritical hours? Well, there's three main strategies. In Europe, there's another. They're looking at mechanical subcooling in Europe. That's not here yet. So we have three main ones that are used. Parallel compression. This is offered by most manufacturers. Adiabatic gas coolers and multi-ejectors, which Hussman doesn't have any plans to use those coming anytime soon. That's just what they tell me. Yeah. The other two we already do use, yeah. So parallel compression, the theory behind this is taking one compressor and dedicating it to handling only my flash gas that comes out of the bypass. So if I combine this with an adiabatic cooler and I limit the amount of transcritical operation I have, I don't need a 15 horsepower compressor for this because I'm only going to be producing a very small amount of flash gas. So if I can throw a 5 horsepower compressor in here, I'm going to save 25% of my power bill right there. Bada bing, bada boom. Adiabatic gas coolers. This is another one, okay? So most condensers are just your standard fans, sucks the air across, condenses it. Basically what we're doing on here, we got some water headers up here. They're going to soak these pads. Now when I say pads, you're probably thinking of something that's very soft and nice, and it's like, this will cut you. This will cut you like an angry ex-partner. You gotta, they are so difficult. They come in these huge, you have to cut them to fit. They get a bunch of cottonwood in them. Anything that can get sucked in there is going to get trapped in there. But they do work. By wetting these pads, the ambient air is drawn over those wet pads. We have regular old evaporative cooling happening. So we're reducing the temperature of the air that we're passing across our coils. And therefore, we can reduce that number of hours we're operating in transcritical mode. And there's that Palm Springs, California. So without it, more than half the time it was in transcritical mode. So pretty much the daylight. With those adiabatic coolers, it's only 5% of the time. So huge increase in efficiency just by utilizing that. Now, I always get the question, what about places like New Orleans or South Carolina or Houston, Texas? And I've been on the roof in Houston and we still have these adiabatic coolers. Most of them are, the ones I've seen are Goodyears, and they are 6 fans, all V-speed. Target wanted a gas cooler discharge of no higher than 95 degrees Fahrenheit. Maximum for the year. I mean, obviously it can be lower. Lower's better. The engineers determined it would need a 20 fan air-to-air cooler to achieve that temperature. But they were able to achieve that temperature and then some with a 6 fan adiabatic in Houston. So it does work. Multi-ejectors, go talk to the Danfoss people about these things. No, this is a Danfoss. Basically, it's going to take the place of our high pressure throttling valve. This is not going to make sense in like Eureka or, you know, like on the coast where it's relatively cool. If you don't have a serious issue with transcritical hour operation, there's no reason to install these. They're expensive as hell. And again, they don't provide those savings unless you're really in someplace hot like Yuma or Vegas or something like that. Again, like I said, Hussman has no plans to implement these in any of our racks anytime soon. Like I said, we partnered with LMP for our transcritical racks. We are Hussman built, soup to nuts. That's in testing in St. Louis right now, in Bridgeton. We make our Cascades in Suwanee, Georgia, and those are Hussman. And then we have the Hussman Protocol unit. We partnered with Emerson on that. We're gonna have scrolls for our low temp compressors, and in a couple years, the medium temp compressors are gonna be scrolls as well, Emerson's. Yeah, scrolls for medium temp. It's happening. Gotta remember, Europe's about 10 years ahead of us on that. So that's why you see all these European companies that are kind of dominating right now. Another thing that we're doing, and it's like far, far away, Panasonic actually makes a transcritical condensing unit, and we're adapting that for the US market, but don't hold your breath. I mean, shit, I could be retired in Mexico by the time that thing hits the market. So, not to say that I'm that far from retirement, but I ain't that close either. So, the reason we're all here is just because of that regulation. So, as the future, you're going to start to see these regulations take effect. The industry's got to change with it. The nice thing about CO2 and propane, they are regulation proof. Administrations change. Sometimes more regulations are implemented. Sometimes they're taken away. Don't really, I'm a fan of regulation. I used to work on the railroad. Norfolk Southern, they took a, Norfolk Southern derailed and killed a town. The American railroads were supposed to have positive train control on all Class 1 railroad leaders by 2010. And they still don't have them. It's 13 years. They've been getting extension after extension after extension. So from a safety standpoint, I'm a big fan of regulation. I don't think they're going to go anywhere anytime soon. But again, we live in strange times, folks.
Transcon's got most of PTC.
Transcon, yeah.
Yeah,
but
I think that's not Transcon or dark territory, you don't. I've worked for BNSF for 8 years.
oh, I worked for that was my shop out in the field, Galesburg. What shop did you work at?
I was out of LA, Colorado, and Wyoming.
Okay, so you bounced around?
Yeah.
Okay. Well, that's good. You never got stuck in Barstow for too long.
Did.
Yeah. No offense to the beautiful town of Barstow, but yeah, I'm just trying to be diplomatic here, people. California. Again, here's a perfect example. And again, this is something, that customers are cognizant about. If you have a major release of a synthetic, it's going to cost a lot of money to recharge that system. The low price of CO2 is very beneficial to that. The EPA estimates that we lose 25% of the charge a year. Is that high, low? You guys have more experience than I. You think it's low? Okay. Well, we erred on the side of caution. Okay. And then this is a fact I just threw in here. There's no test on it. It just kind of blew my mind that refrigeration and air conditioning account for almost 1/5 of electricity usage. And so that's when we talk about solutions for CO2 and efficiency. stores are using half of their electric bill just to keep stuff cold. So if we can save money on that electric bill for them, that's going to be a good thing. Put doors on case, that would, I never really understood that. When you walk, I don't get it. Well, it's a curtain of air. I'm like, yeah, but I can go like this. So, yeah. And also, let's not forget that lots of the developing world, India, China, they have an emerging middle class. And I don't know if anybody's ever traveled to India, but the first thing I'd buy would be an air conditioner because it's hot there. So you have all these people that are putting all this, and that's going to take more and more power. So, well, that's all I got. Thanks for the time. Thanks for your energy. Thanks for your attention.